Quantum communication is a branch of quantum information technology. Quantum communication should not be simply understood as using quantum to communicate. Its true meaning is actually broader. It involves using the principles of quantum mechanics to manipulate quantum states and exchange information between two locations, achieving what classical communication cannot. Just like in traditional information technology, with classical current and electromagnetic wave communication, it predates the emergence of computers by about 50 years. In the development history of quantum information technology, quantum communication has also been at the forefront as a pioneer. It became the first direction to be industrialized within quantum information technology. Quantum communication can be divided into quantum encrypted communication, according to application scenarios and the type of bits transmitted, and quantum bit transmission as two directions, blockchain. The first direction, quantum encrypted communication, is based on quantum key distribution technology, or quantum random number generation technology, which can transmit and measure the state of light quanta to establish an unbreakable quantum key for classical bits, which means our most commonly used digital communication. Quantum keys can be used for encryption, which is quantum encrypted communication, and it is currently the only quantum communication technology that has been industrialized. At present, the industrialized quantum key distribution technology mainly originates from the work of American physicist Bennett and Canadian cryptographer Brassard, who proposed the BB84 protocol in 1984, and some upgrades made to this protocol. For example, the most mainstream decoy state protocols, among others, the BB84 protocol utilizes the quantum mechanical principle that measuring the quantum state of microscopic particles will produce random results. The sender and receiver claim to have an identical random binary key. Meanwhile, the principles of quantum indivisibility and the no-cloning theorem in quantum mechanics ensure that this key cannot be intercepted by any third party without detection during distribution. This means that any eavesdropping will be immediately detected by both parties in communication. As long as the key can be distributed normally and both sides can match it, it is certain that the key has not been eavesdropped on or intercepted by a third party. It can truly achieve a state where no one else knows, only you and I know. This is why the key generated by quantum key distribution in quantum communication security is a set. There are truly random binary numbers, which can be freely chosen at any length, flexibly used for encrypting binary information of different lengths. Due to the true randomness of the key itself, it can directly achieve unbreakable ciphertext using the simplest XOR encryption algorithm. Moreover, XOR consumes almost no computational resources, and its speed can approach the main frequency of the CPU. According to information theory, this truly random key, through a one-time pad encryption method, can resist any algorithmic decryption, including quantum computing, truly achieving unconditional security at the highest level of safety. This is quantum encrypted communication, which has already begun to gradually protect our information security. The second direction, quantum bit transmission, uses quantum entanglement to transmit quantum bits, serving as quantum communication for future quantum computers. It will be applied to the quantum internet formed between future quantum computers. This direction is currently still in the research stage, and it is quite far from being practical and industrialized. Quantum communication is one of the few areas in the field of science and technology where China leads the world. The team led by academician Pan Jianwei from the University of Science and Technology of China has achieved this through the MOSI Quantum Science Experiment Satellite and other large-scale scientific projects, as well as application demonstration projects like the Beijing-Shanghai Quantum Secure Communication Backbone, have enabled China to achieve world leadership in the field of quantum communication from basic research to industrialization. Although quantum encrypted communication has been industrialized on fiber optic networks, its widespread adoption is still far from sufficient because it cannot be used on existing wireless networks. The quantum encryption technology startup, Quantum C-Tech, has introduced quantum encryption technology for mobile device wireless networks, which generates quantum keys on mobile devices through a quantum random number chip. After the initial local distribution and subsequent remote updates using a new key encryption method, quantum encrypted communication can be directly implemented on wireless networks. This solves the last mile problem of quantum encrypted communication. It is hoped that, in the coming years, quantum random technology chips can become standard security chips for mobile devices such as smartphones and VR glasses, truly allowing everyone's private data to be protected by quantum key encryption. Thank you all. I am Zhang Wenzuo. See you next time.